Okay, our last example of a classical failure is the photoelectric effect, described in Atkins 7a. So what is the photoelectric effect? Essentially, it is the ejection of electrons from the surface of a metal by radiation. So I take a UV light, I shine it on a metal surface, and I can measure some current out in space. I eject electrons and can measure some current. How would a classical physicist think about this problem? Well, what you might recall from your physics days is that physicists think of metals as a sea of electrons. So here's my metal surface. It has electrons, 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 electrons. Right? Light is a wave. So I have this incident wave that's coming in on this. There's an electric field associated with this wave. And the intensity of it is proportional to the height of the amplitude of the wave. Right? So if I switch my color, we can draw this more easily, perhaps. Right? This would be some higher intensity wave. And so what you might anticipate is that if I increase the intensity of the light high enough, right, it would shake the electrons, and at some point it would rip them off. Right? So if the intensity is high enough, right, you would start to rip electrons off and eject them. And this is the basic notion. Right? So as you increase the intensity of the light source, electrons are shaken harder by the electric field and they're ejected with greater energy. One thing I didn't talk at all about here was the wavelength of light. And to a classical physicist, this is irrelevant. Right? Wavelength is how long or short a particular wave is. I don't care. All I care about is how high the wave is. Well, you go run the experiment, and here are the observations that are made. No electrons are ejected regardless of intensity unless the frequency of light is above some characteristic threshold. So I can dial up the intensity of light as high as I possibly want, and nothing happens unless the wavelength of light or the frequency is above some threshold. More confusing, if the wavelength of light is above that threshold, right, I can eject electrons with really low intensity light. So I keep the intensity really low, but as long as I'm above that threshold, you can still kick them off. And this is more of a fine-tuned point, but the kinetic energy of the ejected electron increases linearly with the frequency of radiation, but it doesn't depend on the intensity. So this is all confusing, and no one could explain this really very well. The person who came along and explained it was this guy. And I don't know if you recognize that person. You've certainly heard of him. That's Albert Einstein, right? In 1905. I think he was in his early 20s at this point. And he wrote a very famous article, a very famous research paper on a heuristic point of view concerning the production and transformation of light. He had a really simple idea in this paper, which was essentially to say that we think of light as a wave, but maybe we could also think of it as a particle, which he called photons. And the energy of a photon is proportional to its frequency. The proportionality constant is Planck's constant. Right? That was telling us how lumpy energy was. So the important equation here, the one which I hope you all know, is E equals h nu, right? Where h is Planck's constant and nu is the frequency of light. I can rearrange this in terms of wavelength, and you get this 1 over lambda dependence. So short wavelengths, high energy; long wavelengths, low energy. This is not new to you, but I want to show you something which perhaps is. And you will find in life, in general, that there's karma. There's some symmetry involved, right? And Einstein proposed that light exhibits particle-like character. Well, what's the symmetrical question? What's the complementary question? And this is it. It is, do particles exhibit wave-like behavior? It's an absurd question. Here's my particle, it's my pen. If I asked you if this was a wave, you should say no. This is clearly not a wave. So why in the world would I expect anything different for an electron or a proton or a water molecule or whatever it is? Do particles exhibit wave-like behavior? This is a really, really absurd question. And this was so absurd that I don't think anyone really believed it until this paper came out. It's one of those papers which has a title which is so shocking that you think it must be wrong. Right? The title was Diffraction of Electrons by a Crystal of Nickel. And the reason this is so shocking is because of this word, right? Diffraction. Remember that diffraction is the fingerprint of waves. That's how we know that something is waves. And what Davison and Germer are saying is that electrons diffract and therefore are waves. It's absurd. Now, you may think that Davison and Germer were geniuses, and they certainly were in their own right. But it's interesting to look at how they came upon this idea. And you can follow along. I'll read this to you. This is from the start of the paper. The investigation reported in this paper was begun as the result of an accident which occurred in this laboratory in April 1925. At that time, we were continuing an investigation, first reported in 1921, of the distribution in angle of electrons scattered by an ordinary target of nickel. During the course of this work, a liquid air bottle exploded at a time when the target was at a high temperature. The experimental tube was broken and the target heavily oxidized by the inrushing air. The oxide was eventually reduced and a layer of the target removed by vaporization, but only after prolonged heating at various high temperatures in hydrogen and in vacuum. When the experiments were continued, it was found that the distribution in angle of the scattered electrons had completely changed. This was a total accident. You may or may not be calibrated, but if you're working in high temperature vacuum systems with hydrogen gas and something goes boom, that's bad. If you did that in our laboratory, you might get yourself kicked out. But this resulted in a revolution. Right? So let me just show you this. This is what the distribution of their electron angles looked like before the accident. This is what it looked like after the accident. And I'm always impressed by this because I think part of what this reveals is that part of Davison and Germer's genius was recognizing that this wasn't crap. Right? I think if I looked at data like that after an explosion, I would go, oh, we're screwed. The whole thing broke. Right? But they were able to recognize that there was something meaningful and significant going on there. So don't waste a failure. Right? There's a lot of stuff to be learned. So if this suggests that particles have wave-like behavior, how can I calculate the wavelength of a particle? And I'm going to give you the answer here. Right? It's called, well, this is the guy who thought of it. It's Louis de Broglie. He was a French theoretical physicist. And what he suggested is that any particle has a wavelength associated with it, which is given by this equation. Lambda equals h over p. Lambda is the de Broglie wavelength, h is Planck's constant, and p is the momentum of the particle. And I'll give you some problems to work with this a bit in the worksheets, but let me just affirm something to you, which is to say that indeed particles do have wave-like behavior. Okay? The wave nature of particles has been demonstrated in multiple things: electrons, protons, helium atoms, even large biomolecules. And physicists are always working to increase the size at which the wave nature of particles can be observed, right? Like a virus or some microelectronic structure. Right? So there's absolutely no doubt about this. And this is one of the first examples of this shortly after Davison and Germer, where they were looking at the wave character of hydrogen atoms. What you need to remember is here in red. Right? Lambda equals h over p. So the wavelength of particle is inversely proportional to its momentum. If something has high energy, it has a large momentum and a small wavelength. Something which has a small energy has a large wavelength. So the energy of a particle is inversely proportional to its wavelength. And it will turn out, as we'll see in this course, that small things, like electrons, exhibit wave-like behavior on length scales which are critical to chemistry. The reason chemistry happens as it does is because electrons are situated in such a way as to exhibit this wave-like behavior on length scales that are important for atoms and molecules. And that's what we'll talk about in the course. So I will stop here. See you soon, hopefully.